So today we're gonna start talking about the unit circle and the 6 trig functions. So before we can get into the unit circle, we're gonna fill in one of these copies today together, and then I'm gonna have the extra copies for you for practice. I always keep extra blank copies of this outside my office door, and then I'll probably put the file on ELC, but you really wanna practice filling this in, because even though you're not gonna be able to use one on the test, you can still draw one. No one says you can't. And even if you don't want to draw the whole thing, at least being able to sketch the first quadrant is going to help you. And so it's really, really useful to learn how to be able to fill this in, because that way you're going to recognize the angles on it. Because if we ask you to find, like, cosine of 5 pi over 3, we expect an exact answer, and you should recognize that that is one of the angles on the unit circle. So on my YouTube channel, the same one that I post these videos to, I have a separate video that is just the unit circle. So that way you don't have to go back to this class video if you want to see it redone or revisit it. But there's actually a neat little algorithm you can use to fill it in, so you don't have to memorize it all cold. But like if you ask me now what's sine of 30, I can't just regurgitate it off the top of my head. I just know how to sketch it and find it in a couple seconds off the unit circle. All right, so the first thing we're going to do is we're going to talk about the 6 trig functions, and we're going to learn these today in the context of right triangle geometry. So when we're talking about a right triangle, right, we talked about one of these in unit 1. So it's got a right angle, and we're going to define all of our angles by this guy in the lower left-hand corner. So theoretically, you can use either anterior angle. We don't use 90, right, because that's the right triangle. But we usually, when we're doing it in general terms, I like to define the bottom angle, because I want the adjacent side to be the x-axis, because that's standard position. And when we're going to be measuring angles in the unit circle, we're going to be measuring all of them off standard position. And so then it makes a lot of sense to call the base x, the height y, and we call the radius, or the hypotenuse, r, right? But on the unit circle, the hypotenuse of every triangle you're going to create is actually going to be the radius of that circle. So it makes a lot of sense to leave that guy as r. So when you're learning something about using trigonometry, because there are 6 trig functions, there are always going to be 6 rules on how to do everything. So that can be really daunting, and when you get into calculus, you're going to have to learn more stuff, and everything's got to be done 6 ways. But if you really understand sine and cosine, and you can understand how the other 4 trig functions relate back to sine and cosine, if you get in a pinch and you can't remember the rule for cosecant, but you know what cosecant is in terms of sine or cosine, you can rewrite the function in terms of sine and cosines, and then just use the 2 rules for those. So the first thing that we want to talk about here is cosine of theta, all right? So when we're talking about cosine theta, we can calculate it in terms of the lengths of the sides of the right triangle, and we say, well, it's the adjacent side over the hypotenuse. Now, when I was first learning this stuff, I was like, well, adjacent means next to, right? So I used to get confused, because I'd be like, well, this is next to theta, but so is this, right? So when we talk about adjacent and opposite, we're only talking about the legs of the triangle, because the hypotenuse has its own special designated name. So it's always going to be, adjacent is always going to be the leg that is next to the angle, right, excluding the hypotenuse. So if we say adjacent over hypotenuse, well, the way we've defined our triangle, right, that's x over r. And if I solve this equation for x, I get that r cosine theta equals x. And that's really important, because we defined our angle with respect to the horizontal. All the angles on the unit circle are going to be defined with respect to the horizontal. So all the coordinate points on the unit circle, the x coordinate of the point is going to go with cosine of that angle, all right? Now on the unit circle, r is 1, because it's a circle of radius 1. So on the unit circle, it's just going to be 1 times cosine theta. It's just going to give you cosine. But if you're looking at a point on any circle, right? Let's say our circle had radius 2. Well, then if I found a point x comma y on that circle, well, then the x coordinate would be 2 times cosine of whatever angle I was at. So you can actually expand this to circles of any size that we want, And a little bit if you go high enough in math, like if you make it to Calc 3, you actually learn something called polar coordinates, and polar coordinates was where we actually change into r and theta instead of using rectangular coordinates, all right? So sine of theta is opposite over hypotenuse, and for our triangle, that's y over r. So if we solve this for y, right, we now see that the y values of any coordinate point are going to return the sine of that angle. So tangent of theta can be written in terms of sine and cosine. So it's sine theta over cosine theta. If we want to define it in terms of the legs of the triangle, it's the opposite side over the adjacent side, which is going to be y over x. So if you couldn't remember opposite over adjacent, or you couldn't remember y over x, well, if you plugged y over r into the numerator and you plugged x over r into the denominator, you would see the r's would end up canceling and you'd end up back at y over x anyway. So if you're looking at a value on the unit circle, right, and all we have are x and y coordinates, and I ask you to find tangent of an angle, well, then you would take the y coordinate value and put it over the x coordinate value and simplify, and that's how you could find tangent. So then the remaining three, reciprocal, I hope I spelled this right. Spelling isn't good for me today. All right, so if the remaining three trig functions are what we call reciprocal functions, okay? So if you remember, a reciprocal is when you flip a fraction, right? So the first one we're going to look at is secant theta. And secant theta is 1 over cosine theta. Now the way I remember these is the s's and the c's go together. So secant's going to go with cosine, and in a minute we're going to learn about cosecant, and that's going to go with sine. So the s's and the c's always go together. So if secant is 1 over cosine, well then you just take all the rules for cosine and flip them upside down, because that's what the reciprocal is. So it would be hypotenuse over adjacent, or r over x. If you're looking at the unit circle and we ask you to find secant of a value, well then you find the cosine of that angle and you flip the answer upside down. Cosecant is 1 over sine theta, so that's hypotenuse over opposite, and so we get r over y. Cotangent theta is 1 over tangent, and that's easy to remember because they both have tangent in them, right? So if tangent was sine over cosine, then this is going to be cosine over sine. So now you would say adjacent over opposite, or x over y. So all of these are ways we could find cotangent. So a little bit later in the unit, we're going to actually get into the graphs and we're going to talk a little bit more about this, but today we're just going to focus on what these guys are, what the unit circle is, and now I'm going to show you where what we call the special angles come from. So on the unit circle, it is not arbitrary the particular angles that were picked to divide the circle up into, okay? So what we're going to do first of all is we're going to derive these angles, and I'm not going to ask you, and you probably wouldn't be asked on an exam, to derive these angles from scratch, but the reason I want to do it is because we use geometry to derive those angle values, and later in the unit you're going to be doing word problems, and in those word problems you're going to have to sketch a picture, and you're going to have to use some of the very techniques that we're going to use today to derive these. So I want to kind of show you how we come up with these values. All right, so the special angles A lot of people include 0 and 90 in this list. I'm not, because when we actually go to fill in the circle, you're going to see it's just really silly. It's your 0 and 90 are going to be very obvious from the geometry of the circle. So we're going to show where sine and cosine of 45, 30 degrees, and 60 degrees come from. So since the unit circle is radius 1, right, I want to pick some geometric shapes that have side 1, so that way when we derive our triangles, or the sine and cosine out of the right triangles we're going to create, it will correlate directly to what we plug in the first quadrant on the unit circle. So the first thing we want to do is we're going to work with 45 degrees. So we want to start with a square with sides equal to 1. So all 4 corners, or 4 angles inside of a square, are at 90 degrees, right? So in order to work with sine and cosine right now, we need a right triangle. And the way we get a right triangle is we simply use the diagonal of the square, right? And that's going to create 2 right triangles for us. More importantly, the diagonal is going to bisect those 2 angles. So the angles that were 90 degrees are now 45 degrees. So we have a 45, 45, 90 triangle is what we've got. But in order to talk about sine and cosine, I need to know what the hypotenuse is. So we can solve for the hypotenuse of this triangle using the Pythagorean theorem. So the base is 1, right? The height is 1. That's going to equal r squared. So 2 is going to equal r squared. And the square root of 2 is going to be r. So just a little side note, because you're going to be working with diagonals of things in the future and probably later in this unit, right? Really the way you want to think about this is, for this particular square, the diagonal was square root of 2, but really what we're looking at here is 1 times the square root of 2. So if I were to expand this square, make it a little bigger, and let's say it had side 2, right? I actually know that the diagonal of any square is simply its side times the square root of 2. So if we were to plug a 2 in here instead of 1, right, we'd have 2 squared plus 2 squared, right? So then when you add them together, you have 2 times 2 squared. And then when you take the square root, you would get 2 square root 2, okay? So generally speaking, the diagonal of any square has length s square root of 2. So whatever the side of the square is, you multiply it by square root of 2, and that's the diagonal. So the Pythagorean theorem will give you that value every time, but sometimes when you're doing problems or you're looking up a solution online or something, you'll see they just jump to that, and you're like, where did they get that, right? And so once you've done the Pythagorean on one of these a couple of times, you start to see that pattern, and everybody just kind of memorizes that that's what it is, all right? So let's use this now to figure out what sine and cosine are going to be of our angles. So let's do cosine first. So cosine of 45 degrees is going to be adjacent over hypotenuse. And the hypotenuse was square root of 2. Now, you may find a few unit circles online that actually list it as 1 over the square root of 2. But generally, when you look a unit circle up, we like to rationalize those numbers. So way back when you were first learning radicals, your teachers probably told you it's not mathematically correct to leave a radical in the denominator, right? So what they do when they write the unit circle is most of those numbers are rationalized. So one of the things you really need to get used to in this unit is sometimes when you do the algebra, your answer is going to solve, it's going to be perfectly right, but then when you go to look at the answer, it looks different, okay? And so if you ever get in that situation, try rationalizing the denominator and seeing if that fixes the problem for you. But you're going to get answers that are mathematically equivalent but may look different. So what we mean by rationalizing, right, is getting rid of the radical in the denominator. So you do that by multiplying it by another square root of 2, but that means I also have to do it in the numerator. So on the unit circle, it usually looks like this. So 1 over the square root of 2 is equivalent to the square root of 2 over 2. So if we do sine of 45 degrees, well, the adjacent side is 1, right? The hypotenuse is 2. So this is also square root of 2 over 2. So sine and cosine at 45 degrees are the same. And that's really useful to know, because if we're asking you to give you a problem, we give you a triangle and we say find all 6 trig identities, right, of this angle, and the angle's at 45 degrees, well, once you find sine, you know cosine's the same. And then you can do the rest of them off your sine and cosine. All right, any questions about this? Okay. All right, so let's look at 30 and 60. So for 30 and 60, I need an object, right, with all sides equal to 1, but I need to have an angle of 60 degrees. So the most obvious choice is to use an equilateral triangle, because all the angles in a triangle have to add up to 180, and if all the sides are equal, then all the angles are equal, and 180 divided by 3 is 60. So we're going to get something that looks like this. Each one of these sides is 1, and every angle inside is 60 degrees. So in order to figure out what sine and cosine are, I need a right triangle. So in the same way we could use the diagonal to cut across and slice the square in half, right? What we can do on this equilateral triangle is we can slice it down the center, and that's actually going to create 2 right triangles for me. So this upper angle that was also 60 degrees got bisected, so that means this angle up here is 30 degrees. That also means on the bottom that the total length was 1, but now the base of each of my right triangles is 1/2. So does anybody remember what an isosceles triangle is? Anybody? That's has a name, but it's oblique, I think, is what that is, right? But isosceles. Two of the sides are equal. So if 2 of the sides are equal, typically the way we draw them is like we'd say, well, these 2 sides are equal, but the base could be any length that we want it to be. And on an isosceles triangle, if the 2 sides here are equal, the 2 angles at the bottom would also be equal, right? So what's going to happen a little bit later in the unit is you're going to be playing around with a lot of different polygons and geometric shapes. And so you're going to see that you're going to be able to create an isosceles triangle, and you can do what we just did on any isosceles triangle. If you draw it so the 2 sides are on the top, right, you can split it down the center and turn it into 2 equal right triangles, and so it splits the angle at the top, and it's going to split the base in half. And so this is a technique that you're going to actually be using a lot in here. So for an equilateral triangle, it works. It also works for an isosceles triangle. All right, so now what we've got is this little right triangle right here. And we've got to figure out what the height is, right? Because we know 2 of the sides, but we don't know the 3rd side. So I'm going to do the Pythagorean theorem again, but notice now that the unknown side is a leg and not the hypotenuse, right? So when we do the Pythagorean theorem, it's going to be 1/2 squared plus h squared equals 1 squared. So then 1/2 squared is 1/4. 1 squared is 1. 1 minus 1/4 is 3/4. So h is the square root of 3/2. And we're going to need all 3 sides to do sine and cosine. All right, everybody cool with that? Okay. So if we want to do cosine of 60, so cosine says take the adjacent side, so the adjacent side here is 1/2, and divide it by the hypotenuse, which is 1, so this just simplifies to 1/2. If we want to know what the sine of 60 degrees is, well, the opposite side is the square root of 3/2 divided by the hypotenuse, and so we just get square root of 3/2. So we can actually use this triangle to find sine and cosine of 30 degrees as well, right? But what's going to happen when we switch to the other angle? The adjacent side for 60, which was 1/2, is now the opposite side for 30, right? And the opposite side for 60 is now the adjacent side for 30. So what do you think is going to happen to sine and cosine? They're just going to flip and go the other way. So cosine of 30 is going to be the square root of 3 over 2 over 1. So the square root of 3 over 2. And sine of 30 is 1/2 over 1, which is just 1/2. So by switching to the other angle, right, and we're always talking about the non-90 degree angles, but if you're in a right triangle and you switch to the other angle, the values of sine and cosine will flip because the opposite and adjacent relationship traded off, right? So generally speaking, right, if we go back to this picture and I now want to talk about this angle alpha, well, cosine of theta is going to equal the sine of alpha, and sine of theta is going to equal the cosine of alpha. And that will be true in any triangle. So there used to be a question on the homework when we did WebAssign, I'm sure Alex has some questions like this too, where we would give you a triangle and we would label theta and alpha and we would say, find all 6 trig functions for each of these angles. Well, if you computed it all for one and you understood the relationship, the second one you were just switching numbers around. You were just trading off all the values because the opposite and adjacent sides switched for those 2 angles, okay? So the more you fundamentally understand how this stuff works, you can cut the work way, way, way down when you're doing these problems. All right, so let's play with the unit circle. So this is the only class I haven't had to draw this on the board, so thank God for you and me for that, all right? So a couple things about the unit circle. So it is a circle of radius 1, right? So what's the equation of this circle? You know the center, you know the radius.
X squared plus y squared equals 1.
X squared plus y squared equals 1, right? 0, 0, go in for h and k. The radius is just 1. So the equation of this circle, right, is just that. Furthermore, we just talked about that if you're measuring all the angles in standard position, that every point on this circle gives you cosine comma sine of that angle. Cosine's going to go with x, sine's going to go with y. So this thing is actually better than a calculator once you get it filled in, right? So let's look at the first quadrant and label our angles. So in quadrant 1, standard positions right here, the positive x-axis, so that's 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. So what we've done with this quadrant is we split it into thirds, 30, 60, 90. Then we chopped it in half at 45. So that's where these lines come in. So if I were to create a triangle, and what we mean by a triangle, right, if I were to look at 60 degrees, if I were to create a straight line down to the x-axis, I would have a right triangle where the angle with the x-axis is 60 degrees, and that's exactly the triangle we just used. If I drew a straight line down here at 30, the angle here is 30, okay? So the same thing would be true of 45, right? The endpoints on the circle are pretty easy to label because it's a circle of radius 1. So here, right, we should be at 1, comma 0. Here we're at 0, 1. Over here, remember we're in the xy plane, so this is negative 1, 0. And down here, we're at 0, negative 1. So that's why I said we're not really going to bother deriving 0 degrees and 90 degrees because the answer is either 0 or 1 depending on where you are around the circle. Now we actually have everything we need to fill in the coordinate points of all these points on the circle in the first quadrant. So at 30 degrees, we said, well, cosine was square root of 3 over 2, sine was 1/2. At 45 degrees, it was square root of 2 over 2 and square root of 2 over 2. At 60 degrees, it was 1/2 square root of 3 over 2. So we just filled these in by actually deriving every single one of these points. But what if you forgot the derivation, right? Or you didn't have it in front of you? Could you fill these points in without memorizing, right, what the circles or squares and triangles turned into? Okay, and the answer is yes, you can. So there's a pattern. There's always patterns in here. So notice how every single one of those points is over 2. So the denominator, just it's 2 all the time. Okay, unless you're at the 1 or 0 marks, it's always a denominator of 2. But look what's happening in the numerators. So if you pick a 0, right, and I'm going to pick the 0 in the y position, and you find its corresponding 1 on the other side of the quadrant. So if we're in the y position, you want to go toward the 1 that's up here in the y position. And now look at the numerators. 0, square root of 1, which is 1, square root of 2, square root of 3. 0, 1, 2, 3. Then if you pick the 0 in the x direction and count toward the 1 in the x direction, it still follows 0, 1, 2, 3. So even if you can't remember, right, there's a pattern to the numbers, and if you can count to 3, right, you can do, you can fill in the unit circle, okay? So knowing that pattern, right, and there's symmetry in this circle, that pattern will adhere for the rest of the circle. So since we know that this guy right here was found from just evaluating this triangle that we create, well, if I take this triangle and I simply fold it over the y-axis, it's got the same base and it's got the same height. The only difference now is my y value is still positive. I'm still in positive y territory, but the x value went negative. So the only thing you have to worry about are the signs of the numbers, and I mean SIGN sign, right, of the numbers, but you should know what the signs of the numbers are because you're in the XY plane. So it follows the same convention. So if we want to fill in a quadrant just arbitrarily, right, that we don't know, well, I know the denominators in this quadrant are all 2, and I know the x values are negative, so I start by doing the following. I have a negative x coordinate, positive y coordinate, a negative x coordinate, a positive y coordinate, a negative x coordinate, a positive y coordinate. And then I pick a 0 and walk to 1. So if I pick this 0 in the y direction, I walk toward this 1, and so it's just 0, 1, square root of 2, square root of 3, and then I walk back the other way. 0, 1, 2, 3, 0, 1, 2, 3. And by symmetry, this should make sense because this point right here is at the exact same height on the y-axis as this point over here. So they should have the same y-coordinate. This is positive 1/2 because it's to the right of 0. This is negative 1/2 because it's to the left of 0. Right? So we can do the same thing down here. Down here, everything's negative. So I'm going to have negative, right? Negative. All right, and then I'm just going to pick a 0 and walk to 1. So I'm just going to do the y direction first. So I walk down. And then back the other way. So if you know the algorithm, you can draw these things very quickly. It takes longer to actually draw the circle than it does to label it, if you know what you're doing. All right, and over here, right, the x values are positive, the y values are negative. So then I'll take 0 and walk down to 1, and then go back the other way. All right, so without knowing the angle measurements, just knowing the coordinate points, and understanding that the x component is cosine and the y component is sine, well then based on what quadrant you're in, that's going to tell you whether sine is positive or negative. So in the first quadrant, everything's positive. In the second quadrant, cosine's negative, sine is positive. In the fourth quadrant, everything's negative, right? And in the third quadrant. In the fourth quadrant, cosine's positive, sine is negative, right? So then another thing we might ask you is, where is tangent positive? Well, if you know that tangent is sine over cosine, well, the only way you're ever going to get a positive number is to divide a positive by a positive, which would be the first quadrant where everything's positive, or to divide a negative by a negative, and that's only going to be true in the third quadrant. In quadrants 2 and 4, cosine and sine have opposite signs, so tangent's always going to come out to be negative. All right, so we're going to ask you to do like some deductive reasoning about, sine is 1/2 and it's positive. So you have to know, all right, well, where on the unit circle is sine have a value of 1/2, and in what quadrants can sine be positive? Okay, so that's why I said this thing can be better than a calculator, because when you get it all in front of you, and I definitely recommend using it a lot when you're doing your homework, just so you get used to staring at it, and then you'd be surprised how visual your brain will kind of absorb this. All right, so let's fill in the angle. So filling in the degree measurements is actually not that bad, because there's a pattern. And if you know the pattern in the first quadrant, that pattern adheres through all the other quadrants. So we said we chopped the circle into thirds, 30, 60, 90, and then divided it in half. So if you actually look at the angle measurements, what you're seeing is 30 plus 15 plus 15, because we chopped that one in half, right? Plus 30. So that's going to follow all the way around. So I'm going to take 90 and I'm going to add 30. And then I'm going to add 15. Add 15 again. And then add 30. And you can kind of check yourself on this whenever you hit the 90-degree marks, because you should know your 9's timetables, right? 9 times 2 is 18, so 2 times 90 is 180, right? Then in the third quadrant, we're going to do it again. I'm going to add 30, add 15, add 15, and add 30. And same thing in the fourth quadrant. And if you've done this right, you should end up at 360 degrees when you get all the way around. So there's kind of a trick to doing the radian measures, right? So the radian measures are always simplified, and when we give them to you in problems, we're going to give them to you in the most common, like, simplified way, okay? So if you know the radian measures for quadrant 1, it's actually very easy to count around the circle. So one of the things you need to remember is when you count, we don't always just go 1, 2, 3, 4, right? Sometimes when we're in a hurry or we're counting money, we might count like coins and like 2, 4, 6, 8, right? If you're counting nickels, you're going to say 5, 10, 15, 20, right? I was a pharmacy tech for a while. When you count pills, you don't ever count 1, 2, 3, 4. You'd be there all day, right? You count groups of 4, groups of 5, right? So that's what we're going to do to count these radian measures around. We're going to look at the radian measures for unit 1, and then we're going to count in increments of that around the circle. And you'll see what I mean. So there is a pattern in the first quadrant for the radian measures as well. So 0 degrees is going to be 0 radians, and 90 degrees is pi over 2. So everybody should kind of know that right off the top. You can do that conversion very quickly. So the pattern that it kind of follows, it's easier if we go from pi over 2 back to 0. So it goes pi over 2, pi over 3, pi over 4, there is no pi over 5, pi over 6. So 2, 3, 4, skip 5, 6. And if you fill the degrees in first, you now know what every one of those is equivalent to in degrees, okay? So when you count around this guy, the method that I like to use is start with the biggest angles and then work your way down to the smaller angles. So every time you loop around the circle, you're tracing over your previous steps and you can check yourself along the way to make sure you're counting properly. So let's count around in increments of 90 first. So 90 is pi over 2. So if I'm starting around, I've got 1 pi over 2. Then when I get here, I'm at 2 pi over 2, and 2 pi over 2 is pi, because the 2's cancel, right? Then you do it a third time, we get 3 pi over 2. When you do it the fourth time, you get 4 pi over 2, and 4 pi over 2 is 2 pi. 4 divided by 2 is 2. Right? Then I would count in 45-degree increments, right? And so every quadrant split into 2, so there's going to be 8 of those. So 45 degrees is pi over 4, so here's 1 pi over 4, 2 pi over 4 is pi over 2, 3 pi over 4, 4 pi over 4 is pi, 5 pi over 4, 6 pi over 4 is 3 pi over 2, 5 pi over 4, and then 6 pi over 4. Wait, did I do this wrong? Hang on, I did the same thing in my last class. 5, 6, 7. There we go. So 7 pi over 4, and then when you get to 8 pi over 4, you're back at 2 pi again. All right? So the last trip around, we just need to count in 30s. So every quadrant has 3 30-degree angles, so there's 12 of those. So 30 is pi over 6. So 1 pi over 6, 2 pi over 6, simplifies to pi over 3. 3 pi over 6 is pi over 2. 4 pi over 6 is 2 pi over 3. 5 pi over 6. 6 pi over 6 is pi. 7 pi over 6. 8 pi over 6 is 4 pi over 3. 9 pi over 6 is 3 pi over 2. 10 pi over 6 is 5 pi over 3. 11 pi over 6 and 12 pi over 6 is 2 pi. So a lot of times what I used to do on exams was I would draw out the first quadrant because that was easy. I could fill the first quadrant in really quickly. And then by understanding the symmetry, I could easily just fill in the missing bits of the circle as I needed them because I could just count around to the parts I needed. Or some people just like to take a couple minutes at the beginning of the exam and just fill the whole thing in because once you got it down, but just taking 2 or 3 minutes at the beginning of a test to fill this guy in can actually save you a lot of time during the exam because you can just keep looking at it. So you can't bring one in with you, but nobody says you can't draw it. Okay? So this is a very, very useful trick. So there's a couple patterns that I want to make sure you guys recognize here. First thing is there are only 5 numbers in any of the coordinate points around this circle. There's zeros, there's ones, there's 1/2s, there's square root of 2 over 2s, and there's square root of 3 over 2s. That's it. The only thing that changes is the sign in front of them based on what quadrant that it's in, okay? The other thing is the zeros and ones are always together. The square root of 2 is always paired with square root of 2 over 2, right? Square root of 3 over 2 and 1/2 are always paired together. So if you know that and you're doing a problem and you get that sign of some value as 1, well then that means cosine of that value has to be 0 because 1 and 0 always go together, right? If you are told that cosine of some value is 1/2 and they want you to find sine, well you already know it's plus or minus square root of 3 over 2. You just have to figure out what quadrant you're in and pick it out that way. So if you really pay attention and understand some of these patterns that are exhibiting, you can save yourself a ton of time when you're working through problems, right? Any 45-degree measure, right? It's square root of 2 over 2, square root of 2 over 2. It's just the signs change around based on what quadrant that you're in, okay? All right, so that's it for today.